Hey everybody, and welcome to another Jamovi video. In this video, we are going to explore, and I'm going to give an overview of an add-on module. It's called BSS. Here it is, right here. Press the wrong button. BSS, okay? It has its own little module space, and we're going to explore a couple of these. I think I'm going to show you compare correlations and then the outlier detection. Going to open up some data for these two, but we're going to do compare correlations first. Now, it has network analysis. It has input imputation for missing values. It has descriptive discriminant analysis, which is a post-hoc test for MANOVA, which does not exist in base Jamovi. Very important. And then sample size calculations for animals and for a finite population. Not going to explore that, but if you have uses for those, definitely jump in and explore those. How do you get BSS? Well, you go into modules, you go to Jamovi library, you type in BSS, and if you haven't downloaded it, you would say install, you click on that. So Rafael Lambertucci, this is 0.0.9, 0.0.9. Yeah, 2 zeros. This module offers a varied set of statistical procedures for diverse data analysis needs. It's kind of like a mishmash. Features include network analysis, missing values analysis, and data imputation using the MissRanger package, which is an R package that you can put in your R environment. Post-hoc analysis for MANOVA using descriptive discriminant analysis, including its effect size calculation, which is lovely if you're doing MANOVA. Outlier detection using a box plot or modified z-score with adjustable thresholds. We'll explore that. There's some instructions that you get when you choose those. Sample size calculations for finite populations with 2 different formulas, and for experimental design with animals, which is a resource equation approach, has to do with the fact that you have living beings that you have to take care of, and you don't want to oversample, nor do you want to undersample, but you got to make sure that you have the actual bodies for that. Not anything that I do, so I won't be using that part of the module. And then statistical comparison of correlation coefficients, independent and dependent. So we click on that and we are good. So let's go ahead and look at compare correlations first, because you don't need a data set open for this, right? So here we have independent correlations, and it's going to compare your R value of 2 X and Y variables in group 1 versus group 2. And then you can also compare dependent correlations, comparing R of 1 to 2 versus 1 to 3 in one group. But you just set the parameters here and it will tell you what the z-score is and the p-value for that z-score. So essentially for independent correlations, this is doing a Fisher's exact z-test, which is nice. So what you do is you only look for these top 4 if you're using independent, right? It says independent. And then if you choose dependent, then it's these bottom 4 comparators. Okay, so let's go ahead and change our sample to, let's just say 50 each. Okay, we're going to change that to 50, right? And it'll update it automatically over here. Let's say the coefficient for group 1, or the first sample of 50, was 0.53, and the correlation coefficient for group 2, well, let's say, was 0.2. Okay, oops, let's go back to that. I don't know how I clicked over there, but here we go. So we have a comparison of coefficients. 0.53 to 0.23 is a z-score of 1.726 and a p-value of 0.08. Not great, but what if we change this to 0.12? Okay, you can see that I guess that's what happens when I don't click on the actual module. You can see that our Fisher z-test is 2.276 and our p-value is 0.02. So they are statistically different from each other. So that is a quick Fisher's exact z-test. Now, if we wanted to do this one, we would change this to that, and we would go down here. And let's say we sampled 100 people. Remember, this is the only group, right? But we have 3 variables that we are going. So variable 1 to 2, let's say, was strongly correlated at 0.68. Let's say variable 1 to 3 was moderately correlated at 0.36. And let's say variable 2 to 3 was weakly correlated at 0.14. Let's say that. Okay. So the correlation of 1 to 2 is 0.68. Correlation of 1 to 3, 0.36. Correlation of 2 to 3 is 0.14. So our t-value for this is 3.211, and our p-value is 0.002. So this is telling us that these correlations are similar enough, okay? They're similar enough, 1 to 2 and 1 to 3, similar enough that we need to make some changes, okay? So, and let me show you if we make this 0.14. Oops, there we go. Super. Oh, wait, I'm sorry. The t-value is telling us that they are not the same, because if I do 0.68, let's do 0.6. Sorry, I had that backwards. So the variable here is the t-test here is telling us if it is statistically significant, it is telling us that they are not related to each other. If they're not significant, like it is now, they are related. So, and you can see that here, but maybe you don't know. Maybe you had a sample of 1,000, right? So you can see that changes quite significantly, even with a 0.08 difference. So very important there to recognize. If I change this to 0.63, for example, it's even worse, it gets even better, right? So that's how you compare. You'll probably use the independent one a lot more often than the dependent one. There are some use cases where that might be where you might use correlation coefficients. We'll see, but independent correlations is where it's at. All right, let's change this to outlier detection, IQR, right? You need a data set open for this one. So actually, let's open, not Vig plots. Let's open Let's open Phobia, for example. This is from Sarah, module that you can download. Let's make it bigger. Let's go to BSS over here. Let's use the IQR method. Okay, so variable. Let's say anxiety. Let's see if there is a box. So this is a box plot for anxiety. So it will, if we use 1.5 IQR, it's saying that we have no outliers. So this is also going to suggest that we don't have any outliers for 2.2, I mean, or using the 3.0 method. Ooh, just got to scroll all the way over there. But we can also add in all of these. Let's add in all of these to add in these variables. So, oh, it's kind of hard to see. Okay, so no outliers for 3.0 for any variables. But we do have one variable with a 2.2 IQR. So it's greater than, so this would be EACTBL. I don't know what that is. That's what it's saying. And then we have two variables using 1.5 IQR. This was the first method that I learned when I was in stats. So that is 1.5 times the interquartile range. So is it, so just to, in case you're unclear, this box right here represents the interquartile range. Dark line is the median. And then we have the 25th percentile as the bottom part of the box and the 75th percentile as the top part of the box. And then these are whiskers as they are referred to. So box and whisker plot is the original name of this plot, right? So here, and what it does is it plots these. So this is 1.5 times the 75th percentile value or times the 25th percentile value in the opposite direction, right? So this is the fence, lower fence, upper fence, lower fence, upper fence, right? So these are the values of those, right? And so it can, by virtue of that, it can tell us if there are values. So these are the number of values in the variable that are above or at or above 1.5, the interquartile range, or below, I should say, or 2.2 times the interquartile range, right? So like I said, we had one value in EACTBL that was 2.2 times, and we can see that is actually below, right? It's a value of 30, okay? And then here we have three values in ThoughtBL and two values in EACTBL that are 1.5. Okay, 1.5. So we actually have outliers in both directions for ThoughtBL. That's what these three values are. You can see that two of them are overlapping each other. 23 and 22 is what it looks like. And then we have a value of 3, right? So yeah, there you go. That is the interquartile outlier detection. Oh, I have that on there. But you can also use the modified z-score method. Okay, so here we go. This is the second one, and this is what I teach my students. I just tell them, calculate your z-scores, and if it's greater than 3, then you probably have an outlier. But as you can see, there are various methods for using z-scores to determine what is an actual outlier, right? And so I'm going to use ThoughtBL in this, but let's go through these guidelines here. These are conventions, and they are found in various literature, right? So the first one is in the literature is Iglowitz and Hoagland, 1993, using a z-score of 4. Okay, suitable for large samples, preventing excess removal of naturally extreme values, right? You don't necessarily want to say, oh, that's an outlier, get rid of it, like the interquartile range one is, so you don't necessarily need to do that, okay? They also suggest the 3.5, which is what I learned. 3.5, a z-score of 3.5 or greater, or a z-score of negative 3.5 or lower is where you're going to, since it's the same paper from these guys, Iglowitz and Hoagland, the most widely recommended standard. And it's useful for all sorts of variables, okay? Scale variables, interval or ratio scale variables, okay? So that's 3.5. And then threshold 3.0, coming to now a decade later, 2004, 2.5 to 4.5, used for machine learning. Hodge and Austin suggests machine learning or exploratory analysis threshold can be adjusted as needed, right? So you can choose any value within 2.5, 4.5. And then just a few years ago in 2018, Lee's et al. And Lee single paper. This doesn't make sense. Lee et al. 2018, used for more conservative contexts, so psychology, social sciences, is 3.0. I actually learned both of these after I learned this interquartile range, and I actually tell my students, 3 is probably the better one. So let's put ThoughtBL in here. I don't need a grouping variable, it's fine. Okay, no outliers detected within the specified threshold. So we've got ThoughtBL, right? And we heard that, we saw that we've got 1.5 and 2.2. These are multipliers to the interquartile range. But let's say if we change this to 3.0, if it does it, nope, still undetected. Let's change this to 2.5. Nope, still undetected. 2, there we go. So if we were to use 2, which is not a good idea, 2 standard deviations, not a good idea. But in ThoughtBL, it's saying, and it gives you the row number, and it gives you the z-score for it, right? And these aren't, so there are 3 in the negative and 2 in the positive direction, and gives you the row numbers. And you can filter those row numbers out by using the filter function in data. We can filter those rows if we need to, right? So we can take that out. That's an extreme. This is extreme. You would not use 2. And so if I did the most liberal selection here, there aren't any. So this data set doesn't have too many variables. So that is the BSS module that I'm going to show in this video. You can use, I'm not familiar with misranger imputation, but I'll go ahead and open it up just to show you. So if we had a missing value for thought BL, for example, it would tell us what the imputed data was and is. But I'm not familiar with it enough to know why it's not showing anything, because it says it's shown in the table, but nothing happened. So, there you go. And that's what I'm going to show in this one, right? Compare correlations, data handling, and then these two you can explore by adding it to your Jamovi. If you have any comments, questions, suggestions, other feedback, please leave those in the comment section down below. Thanks for watching. I'll see you in the next one. Bye.